How much can we really understand the human brain? It's a big mystery still. It's just a bunch of electrical signals going on, and we can't really interpret it very well in terms of just doing this. It seems so simple to all of us. All of us can do it, but somehow, for some reason, we just have no idea how it's being processed in here, and then the command is sent to do this. What I do is to integrate the field of neuroscience and the robotics together and call it a field neurobotics. And in the field of neurobotics, what we do is to use robots to understand, rehabilitate, assist, and enhance humans' neural control of movement, which is in general how the brain controls our motion. So what I would really like to do is, given that my research area can have impact on disabled people, I would love to start a non-profit organization, or even just maybe for profit, to get the robots out there for people who would benefit using it. Just they don't currently have them available to them, and it would be great to have a way for me to get it out there through some tangential meaning than just my research and teaching. 10 years from now, I would like to look back and say, because of this exposure, now this field is richer than then 10 years ago.
Welcome to this presentation, MacArthur Fellows who are changing the world. My name is Peter MacDougall, and it was my privilege to serve as the president of Santa Barbara City College from 1981 to 2002. 21 challenging and rewarding years of working with SBCC's exceptional faculty, staff, and board of trustees with the shared objective of developing an outstanding community college. It is a thrill to be back on campus for this most auspicious occasion. I sincerely thank Superintendent President Dr. Andrea Serban for inviting me to provide a welcome for an event that has such significance to the Santa Barbara City College community. Santa Barbara City College identifies 1909 as the year it was founded. On this, the cusp of the centennial year, I can think of no event that could provide greater validation of the college's past and the potential future value than today's celebration. Our educational systems at all levels exist because of the fundamental belief that through a system open to all, the potential of individuals and our collective potential as a society will best be realized. When we review the achievements of today's presenters and the substantial societal benefits resulting from their work, one could legitimately ask, could there be a more vivid validation of this belief in education? Certainly today, the SBC community basks in the glow of the excellence and notable achievements of our two former students. Now retired Professors Michael Mallon, Jim Jolka, Mike in mathematics, Jim in chemistry, and current faculty members such as Dr. Larry Friesen in bioscience and others still teaching at SBCC, I'm sure are pleased and proud to have played a part in the rigorous academic journey and success of today's presenters. I hope and expect that for Dr. Belcher and Dr. Mutsioka, today's visit rekindles many positive memories of the years at SBCC, and specifically how those years on this very special campus may have contributed to the confidence and originality reflected in their nationally, if not world-renowned, academic achievements. Dr. Serban will be introducing our returning alums. As mentioned earlier, it is my privilege to provide a welcome, and I will do so. Welcome to Santa Barbara City College's exceptional faculty who deliver on the promise of college through your daily work with students. I am confident you will be reinvigorated by today's presentation and how it exemplifies the impact you may have on the lives of your students. Welcome to the SBCC trustees, administrators, staff and friends and donors of Santa Barbara City College, who in very substantial ways support and encourage that margin of excellence for which Santa Barbara City College is known. Welcome to our reason for being, current Santa Barbara City College students, who I believe will be inspired by knowing the two individuals who are today sharing the brilliance of their achievements with us, once occupied the classrooms you are now fortunate to be in. And finally, welcome to Drs. Belcher and Matsuoka, whose individual and collective achievements so forcefully validate the highest potential of our educational systems. Thank you, and Dr. Serban.
Thank you, Dr. McDougall, for such a warm and great welcome message. And I would also like to recognize President Emeritus John Romo, who has joined us. I thought he was there. I would also like to welcome you all to this very special event. Our guests this afternoon are truly exceptional, and I'm honored to introduce them to you. Dr. Angela Belcher is Professor of Material Science and Engineering and Bioengineering at the Massachusetts Institute of Technology. She was named a MacArthur Fellow in 2004. Angela, whose research has earned her numerous national awards and recognition, is the leader in the innovative field of nanotechnology. And there is a particular reason why Angela chose this field. She's a vegetarian, and she wanted a field that involved no animals. So what better field than nanotechnology? One of the most visible of Angela's honors was being featured on the cover of Forbes magazine in July 2001. She appeared in the forefront of the photo, followed by a lineup of 4 other experts in the field of nanotechnology, one more renowned than other. Gerd Binning, Nobel Prize winner for development of the scanning tunneling microscope, Stanley Williams of Hewlett-Packard, Mark Reed of Yale University, and Harold Craighead of Cornell University. The year before the Forbes article appeared, Angela was one of 30 scientists nationwide to be honored by President Clinton at the White House with the Presidential Early Career Award for Science and Engineering. In August 2002, the American Chemical Society named her one of the 12 women who will have the greatest impact on chemistry in this century. Dr. Yoki Matsuoka is Associate Professor of Computer Science and Engineering at the University of Washington in Seattle. She was named a MacArthur Fellow in 2007. She's one of the leading pioneers in the emerging field of neurorobotics, a discipline that merges neuroscience with robotics. The caliber of her research has won Yoki national recognition, including the 2004 Presidential Early Career Award for Scientists and Engineers, the highest honor bestowed by the American government upon upcoming scientists. She was also named as the Anna Loomis McCandless Faculty Chair in 2004. She has presented her research at national conferences, and recently she was featured in a television segment on Nova Science, now on PBS. Besides their brilliance and tremendous accomplishments, Angela and Yoki have a few other things in common. Both wanted early on in their lives to become professional tennis players. They would have probably made more money. Both went through the rigorous discipline of the sport and both suffered from tennis injuries. And while Angela never won at Wimbledon as she wanted, she selected another great goal to win a Nobel Prize, which I'm sure she will. Yoki played tennis for SBCC and was selected Scholar of the Year for the state of California Community Colleges in 1991. Her trophy, a large metal plaque, is in display case in the gym. We are holding on to it. It may save the college from this budget crisis later on. Yoki took a scientific interest in her injuries. She became a mechanical engineer, neuroscientist, bioengineer, robotics expert, and computer scientist all in one. Angela and Yoki are both mothers of very young children. When Yoki was informed about her MacArthur Award, she was nursing her new baby, her son, who is now 1 year old, one of her 3 children. Some of us can barely take care of ourselves, let alone achieve so much and have 3 kids. Angela is the proud mother of her son, Braz. Angela's innovation and creativity in various scientific fields has been evident since her days as a straight-A student at Santa Barbara State College. She was on the President's Honor Roll for all 4 of her semesters at SBCC between 86 and 88, finishing with a GPA of 4.0. She was the winner of the prestigious President's Scholarship, the Organic Chemistry Award, and Biological Science Award. Yoki was also an almost straight-A student. It is hard to understand why she got a C in American government and politics, and I'm going to check who that instructor was. She was really upset about the C, but in spite of that, she liked the college so much that she encouraged her own mom to be a student here a few years after she attended SBCC. And her mom was an international student and F1 visa, and Yoki is almost international, but we didn't charge her our international student fees because she became a permanent resident by the time. Yoki, too, was on the President's Honor Roll for all 4 of her semesters at SBCC between 1989 and 1991. We believe our college has had a significant impact on Angela and Yoki, and anyone holding a different opinion, please keep it to yourself. If Angela had never attended SBCC, she would have been for sure tremendously successful anywhere else, but likely in some other area. Her invention and development of the Belcher technique of using viruses as builders would likely not exist. Her virus work started at UCSB on a strong science and math foundation received at our college. If Yoki had never attended SBCC, it is perhaps unlikely that the robotic hand directly controlled by the brain would be as advanced as it is today. It is certainly no doubt that great mentors and faculty had contributed to Angela's and Yoki's exceptional success. And although there are many individuals who should be individually recognized, I would like to take a moment to recognize James Holka, SBCC Professor Emeritus of Chemistry, and Michael Mallon, Professor Emeritus of Mathematics, who are with us today. And Jim and Mike, could you just please stand up for a second and be recognized? One of our greatest satisfaction of college presidents is to brag about the success of our students, and we do that constantly. In 2002, Peter nominated Angela for the Distinguished Alumni Award given by the Community College League of California, an award Angela won. I nominated Yoki this year, and I would like to present to her this certificate of recognition for her outstanding achievement, which is signed by Scott Lay, President and CEO of the Community College League of California. Along with a red SBCC bag of even higher value. And because we thought neither Angela nor Yoki would want or have room in their offices for one more trophy, We are dedicating to each of them the very first 2 tiles in the brand new Hall of Fame for distinguished SBCC alumni on the Alumni Plaza by the bookstore. This way, they will be a perennial presence on our campus and inspiration for many of generations to come. At the end of the program, I would like to invite you all to join us for a reception in front of the theater to greet and celebrate the success that both Angela and Yoki have achieved, and in recognition of how proud we are to name them our own. We will also have towards the end some time for questions, so without further ado, I'm inviting Angela to the microphone.
Well, I'm very, very choked up. I'm very happy to be here, very honored to be here to help celebrate the centennial and to speak to my former teachers and the great students here at SBCC. I do have to make a comment about the Nobel Prize that I mentioned. I don't really know how that got out, but I put it in a scholarship application because I thought the committee, who would reject someone who said that one day they were going to win the Nobel Prize, because so I didn't really have that aspiration, so I just thought it would be too hard to turn down, and I actually did get that, so might be a good technique to use. But it really was here that I fell in love with science, and it's often quoted that one day I really fell in love with molecules, and that's completely true. It's really driven a lot of what I do. I fell in love with the idea of large molecules and in solution and interacting with their environment, and it's really driven a lot of most of all the science and engineering that we do currently in my lab. So I'm very, very grateful to the faculty members. Jim Holka really encouraged me in freshman chemistry, and I remember really struggling on batteries. Do you remember that, Jim? You remember everything. And now I'm considered a battery expert, and so I really appreciate that. And Gary, I was sitting in an organic chemistry seminar. It was yesterday, and I was on the edge of my seat. I was so excited about the reactions that I was looking at, and I was thinking about you. So again, I really appreciate all the support that I had. So in order not to get choked up anymore, I'm going to head straight into science here and tell you a little bit about what I've been thinking about since I left here several years ago. What my lab is really interested in. So I run a lab at MIT of about 25 people that are PhD students and postdocs and then undergraduates. And the main focus of our research is understanding how nature makes materials and borrowing those ideas to work on what we like to say nature hasn't had the opportunity to work with yet. And I'll talk about some of the applications that we're working on. So I called this From Nature and Back Again, Giving New Life to Energy, Electronics, and the Environment. So it really is the interface of many different disciplines: chemistry, material science, biology, biological engineering. And we like to think about the interface between these disciplines because a lot of our work is based on how abalones grow shells. And these are red abalone that were found right off the coast of Santa Barbara. And I'll talk a little bit about abalone as a material. But an abalone doesn't think, oh, I'm a chemist, I'm going to build it this way. I'm a biologist, I'm going to build it this way. It's what do I have in my environment to make the best material for my function? And that's what we're interested in doing. And I'll tell you a little bit about how we think about this. The main thing that my research group is interested in is we call it genetic control of materials. Again, here's an abalone shell. An abalone shell is a biocomposite material. It's 98% by mass calcium carbonate, 2% by mass protein. Yet it has really many exquisite properties. It's 3,000 times tougher than its geological counterpart. It's made in ocean temperatures and ocean pressures without adding toxic materials back into the environment. We think that's an incredible design idea. Let's make something in a non-toxic way. So a lot of our work is based on that. But something that's more interesting to us is when a male and a female abalone get together, they make millions of offspring. They pass on to that offspring the genetic information that says, this is how to build an exquisite nanomaterial. And so that's what we're interested in. Diatoms, too, which are made out of glass, SiO2. So this is glass that's made in the ocean. And they also pass on their genetic information. This is how to make glass, but this is how to make glass in a really specific three-dimensional structure. And every time they pass on this genetic information, you get another exquisite structure at the nanoscale. And so what we focus on is, can you give genetic information to a solar cell, or can you give genetic information to a battery? So that it has a code that says, this is how to make a battery. And so it can assemble itself. And can it have the possibility of evolution where the battery can get better as a function of time? And that's some of what I'm going to talk about. So when we think about future technologies, we started about 4.5 billion years ago to the beginning of Earth. It only took about a billion years to have the first life. And it was, this was organisms that were replicating, eventually have organisms that were photosynthetic. But it wasn't until about 500 million years ago during this time period called the Cambrian geological time period where there was an explosion of life and our organisms started making hard materials. So before this time, they were already doing really tough things: photosynthesis, life, replication. Why weren't they making hard materials? That's what we wanted to know. And so the answer is pretty much opportunity, that it was during this geological time period there was increased calcium and silicon and other inorganic materials in the ocean. And now all of a sudden they had this pressure to take these ions and make them non-toxic, and they started building hard structures. And so through evolution, it was about 500 million years ago that abalone started making shells, but it took them about 50 million years to get good at it. So most of the graduate students in my lab are there for about 5 years. And so we started thinking about how do you come up with a rapid way of trying to get organisms to make solar cells or batteries. And that's what I'm going to talk about a little bit today. And I should say that my first company that I founded was named Cambrios Technology. It's named after the Cambrian geological time period. My second company is called Siluria Technology. So all my companies now are named after geological time periods. And they're so long that there's always something significant that happens during that time. So I should point out my favorite biomaterial. This is my son, Brazos. I gave him the genetic information that says this is how to build bones, this is how to build teeth. But anyone that has had a 2-year-old know they're very complex organisms. And I should say he's standing next to his favorite biomaterial, which is the Triceratops. So we started thinking about what is a simple organism that you can use to start getting it to use a new toolbox to make materials that are important to me. And so we started working with viruses and bacteria and now yeast, trying to genetically engineer them to have a new function, build a battery, assemble a battery. And this is just you probably don't see very many of these here, a snowflake. One of the things that's interesting about snowflakes is they're self-assembling systems. So there's a nucleus at the center of an ice crystal that forms this really exquisite structure. And so what we're looking for are nucleuses that are nuclei that you can have that don't build a snowflake but can start self-assembling electronics. So if you have the right information, can you start assembling interesting electronic materials under biological conditions? And so a couple of years ago, I was asked to give a talk in Washington about what I thought the biggest challenges in material science are. And I took this very seriously, and it was a couple of years ago now, and I put it together. I said, I'd like a material that's self-assembling. I'd like a material that's self-correcting and self-healing, one that grows its own template, recycles its own template, and only grows to the desired length and diameter and stops. I'd like to only use environmentally benign precursors and solvents, room temperature and pressure, and generate little waste. And so when I gave this talk several years ago, there was starting to be giggles in the audience, and these are really people that were much more powerful than me and professionals, and they said, wow, that's a pretty big, long laundry list. Why don't you just pick one thing? But if you think about it, biology's already accomplished all of these things and how it makes materials. And so that's what we're focusing on, is giving biology the opportunity to work with the rest of the periodic table. So organisms like eukaryotic cells, which could be yeast to humans, or bacteria cells, what we want to do is actually convince them to use a new toolkit to start building materials that are interesting, electronic materials. So this is the reaction vessel where life came from. It's the ocean. These are some of the ions and atoms and molecules that are in the ocean. And we think life did a pretty good job. We think biomaterials, humans, abalone shells are pretty good. But we think that life could have done better if it had more opportunity. It had this opportunity 500 million years ago. Let's give it the opportunity again. And so let's see what it can do. Here's some natural biomaterials. This is a coccolithophorid. It's a unicellular algae made out of calcium carbonate. This is a 1 micron scale bar here. This is an abalone shell that if you cleave this and you look at an electron micrograph, you'll see it's actually made out of these little tablets, these nanostructured tablets of calcium carbonate that stack on top of each other to form this brick wall-like structure. This is from an undergraduate project that I worked on diatoms made out of SiO2. And there's magnetotactic bacteria that have small single-domain magnets that are used in navigation. So all of these are made in ocean temperatures using non-toxic precursors. This is just showing you what an abalone shell looks like, a little bit higher magnification. There's an organic matrix in between here. So the organic matrix is actually key to controlling the nanostructure, and it's key to making a really exquisite material. And so only 2% by mass, but this is the difference. This 2% by mass is the difference between an abalone shell and chalk. And you can take chalk and easily snap it between your hands, but abalone shells are actually quite difficult. Well, the key are proteins. The proteins that are actually involved in growing these materials. And many of you know that there's basically 20 amino acids, and these amino acids that make up proteins differ from each other based on their chemical functionalities. And it's these chemical functionalities that are the whole key to controlling calcium carbonate, controlling silicon, controlling bones. And that's what we decided to look at. So here's kind of a mechanism of how a shell grows. There's this thing that looks kind of like a birthday cake is 2 calcium carbonate tablets that are nucleated and controlled by these little squiggles, which are proteins. The combination of these proteins actually help the tablets grow through these organic matrix layers that look like this. This is a tip of a growing pearl, actually, where the length of the diameter of these tablets haven't grown out to their full extent yet. But this is the mechanism by which biology uses to grow inorganic materials. Now again, if you want to think about how to make things on the nanoscale, so on the scale of a billionth of a meter, why don't you start with things that are already really, really small? Why don't you use a toolkit of things that are really small? And so this is actually just showing you a scale structure. This is about 100 nanometers, across. This is about the size of some of the current electronics in your computer and in your cell phone. And this is DNA and proteins showing you how much smaller they are than your current electronics. And so our idea was start with things that are really small and convince them to start growing and assembling useful materials for electronics. So again, going back to the periodic table, nature has chosen calcium in the form of calcium carbonate and calcium phosphate, silicon in the form of silica, and some iron, Fe2O3 or Fe3O4, but really hasn't worked with this part of the periodic table or this part of the periodic table. It's hard for me not to throw out questions because that's the way I teach. But no quizzes today. But you know from your undergraduate biology classes that transition metals are really, really important in biology, but they're usually as single atoms or maybe a really small cluster. You don't see them as inorganic crystals. So biology has the ability to work with that part of the periodic table, but hasn't chosen to do so for larger structures. So the idea is that in an abalone shell, for example, there's a protein matrix that has alternating negative charges that come from carboxylic acid groups. Those negative charges can grab calcium out of solution in the ocean and start putting down a layer of calcium, and then carbonate, calcium, and carbonate. So it acts as a nucleation point to start growing materials. And so what we decided to do was, what if you take any generic protein with any generic inorganic material and put these together? Can you find a protein that matches anything on the periodic table that you're interested in, and then use it to grow something useful? And so the idea comes from, goes back to the vegetarian point, was that everyone knows that you have antibodies in your body, and antibodies are really specific for small molecules and proteins that they can recognize and bind to. And we wanted to use those millions of years of evolution and combine them with man-made fabrication to come up with something we call evolved hybrid materials. So it really is in the interface between living and non-living. How do you give living things the ability to start growing non-living structures? And so when we first started thinking about this, again, we said, how do you find the right molecule to meet that interface? It took about 50 million years for biology to do this.